We don't want that to occur. Okay, so this is where y'all tell me where to go. What do you want to look at? What do you want to review? You want to go eat pizza? You go eat pizza?
I have an issue with determining.
We can call pizza in and eat it in here. I don't want to have pizza delivered. Heck, which test or?
It's not really a test, it's an overall question.
Okay.
Determining orders, like first order, second third order, I'm still.
All right. Let's see if we can find a problem like that. So I pulled up just so we can cover a broad range of material. Exams 2 from 2019, 2018 are very similar to this year. Same content. Going back before that, we were covering different materials. So if I look at exam 2 in 17 and 16, it has the first half of it is material that is dealing with the intermolecular interactions and solubilities and things like that. But then you get about halfway through the multiple choice, it switches gears and gets in kinetics. Exam 3, you've got to go into exam 3 to get into the. I should do that, but you got to get into exam 3 to actually see the stuff that's in the equilibrium chapter. So I opened both exam 2 and exam 3 for those previous years. Let's look at if we can figure this one out. All right, so here is we'll start with this first one, and we'll do a couple of these. Okay, so this is problem 19. It says determine would be exam 2 from 2017. So it's problem 19, exam 2, 2017, if you want to see. It says determine the rate law and the value of K. So to determine the rate law, the first thing we got to do is figure out what the order is. So how is the reaction changing? So there's one reactant. So the rate is equal to K times the concentration of the reactant raised to some power. And our question is, what is the power? That's the order we're trying to figure out. So if I look at how it changes, I'm looking at the ones where it increases some amount. So I gave you 3 different concentrations, initial concentrations, and we want to try to find what the rate change is. So if I can find my calculator. Okay, so which concentrations would we use to try to figure out what the order is? As 1, 2, and 3. If I take and look in what's the relationship where the concentration increases, you could use any of the pairs, but 1 and 2 are so close together, there's not a big change in concentration. That's not very useful. But if I look at the second ones, between 2 and 3, the increase in concentration is 2.67 times. All right, and if I look at the change in the rate, I see that it increases 2.65 times. So that's almost a 1-to-1 relationship. So the fact that you increase the concentration by a factor and the rate increases by the same factor, that tells me that this is first order.
So how did you get that precise number? Because what I would do is top 0.084 times 2, and obviously it wouldn't be that number. So how'd you get 267?
I just divided it into it.
Oh.
So I took the higher concentration, divided it by the smaller concentration.
Okay.
Just because I could see it wasn't quite 3.
Yeah.
It wasn't not 2. So when the concentrations, most of the times we see problems, and we'll look at one like that, it's you double it or you triple it, take your calculator. But this one it wasn't. So you just got to find out what it is. And if we looked at this one, we'll see how close this one would be to working. So if I looked at this one, if I look at the higher concentration and it's 1.1 times the concentration, 1.11. And if I looked at the ratio of the rates, it also comes up to exactly 1.11. So any pair would work. They're just not always even numbers, and that's fine. Sometimes it's more obvious if they are. So just to answer the second part of the question, once we've determined the order, then you could use any of them to determine what the value of K is. Okay, so what I would do is choose reaction number 1 just because it's the first one on the list. And I know that K is going to be the rate divided by the concentration now to the order, which we know is first. Okay, so I would just take the rate, 4.48 times 10 to the minus 4th, divided by the concentration. And that gives me the rate constant. So now this is the value for K. We know the order's 1, so C's our correct answer.
So a second order, how would that change?
Well, if it were second order, the only thing it would change is when I solve this, this would have to be squared, and this would have to be squared in this portion of it. Yep. And we'll do one like that. We'll find another one. Okay, any other questions on this one before I do another example? Okay, let's go look what else we can see what we find. So on that same test, let's see if there's one at the back of the book or back of the problems. There's another one. All right, this one has multiple reactants, so let's take a look at it. All right, so fluorine plus 2 Cl2Os yields some products. So we've done 3 sets of experiments. We change the concentrations, and we look and see how the reaction varies. Okay, so when I've got multiple reactants, just like we did in lab, we need to hold one reactant the same concentration and vary the other. So we're looking where the pairs where things change. So on experiments 1 and 2, what happens is the fluorine concentration stays the same, but the concentration of the Cl2O increases by a factor of 4. It increased concentration by a factor of 4, and I need to find out what's the change in the rate, and I can see that that's 20 divided by 5. That's also a factor of 4. So that tells me with respect to this reactant, so rate is equal to K times the concentration of each of the reactants raised to the respective powers. So with respect to this reactant, 4-fold increase in concentration, 4-fold rate, that tells me that's the first order. And that's the reason we can't look at the stoichiometry. We've got to look at the actual data. All right, so now we know what the order is with respect to that one. We look at the other side where this concentration, the Cl2O, is held the same, and the concentration of the fluorine changes. So between 1 and 3, the concentration doubles. So if I look at it's double the concentration, and now I compare the rates between these two. So 0.5 and 1, it's double the rate. So that tells me that this one is a 1 as well. So now I could use any of them the same way I did on the previous problem. I could plug in and I could find out what the value of K is. So the rate expression is with everything, including the value for K. So same way we did on the other one, we need to find out what K is. So K is equal to the rate divided by the concentration of the reactants raised to the respective powers. And I'm just choosing the first one, so 5 times 10 to the minus 4th. And the concentrations are 0.05 and 0.1, and that's a number, whatever it is. One. Unless I did my math wrong, that's exactly 1. So that means that the rate would equal to 1 times the concentration of the fluorine times the concentration Cl2O. So where did you have to put a 1 in there? No. Anything multiplied by 1 is still the same thing. So it would just be, the only thing you'd have to put is the rate is equal to the concentrations to the first power. Make more sense? Okay, flick it back a little bit.
Before we switch off that, so the fluorine, if it was 2 times, but let's say the rate was 4 times, would that be a second power?
That's correct. Yeah, so if this would have came out to be 4 times as much, that would be second order, which would be second power when you write it in the rate expression. Okay, so what else? What other kind of problems? Or specific problems?
Can you look at problem 7 on exam 2, 2008?
Okay, tell me if it looks like this.
Yes, sir.
Okay. All right. All right, so we did some problems like this on the clickers and in class. So it says you've got a balanced reaction, determine the rate with respect to a particular component, and in this case, it's with respect to the SO3, which is a product. So the way that we wrote the rate expressions is that rate is equal to, and then if it were a reactant, we put a negative sign in front of it, 1 over whatever I'm going to put SF, stoichiometric factor. So that's whatever the stoichiometry is in front. The change of the concentration of that species divided by the change in time. Now this is if reactant. And then it is a positive if it's a product, because that means it's going to be being made in the system. So if we look at the particular one that we have in this problem, we're looking for the rate with respect to a product. So it's going to be a positive, and then the stoichiometry is 1 over 2, stoichiometric factor is 2, change in concentration of that substance, the SO3, divided by the change in time. So looking at choice B. Does that make sense?
Yeah, I remember it now that you did it.
Yep. Okay. What else? Ice. Okay. So you have a particular problem? No. Yeah. All right, let's go to the most recent and see if we had a ice problem in 2019. All right. So rate. Okay.
Number 31.
Say again.
Is number 31?
Okay. We'll do do 30. 31's really not an ice problem. It's writing out the K expression, but we can do that next.
Oh, no, I was saying it's 31 of the ice problems.
No, it's just writing out the K expression. So you don't have to solve the equilibrium now.
No, I know. I was saying it's 30 in ice problem.
30, yes.
Yeah, sorry.
I'm hearing 31 for some reason, and I'm admittedly deaf. So. Trying to get that unhighlighted. And successfully, I'll leave it highlighted. Okay. So when we solve the ice, we need to write the reaction out. CH4 plus 2 H2S yields CS2 4 H2s. So initial, change, and equilibrium. Okay, so it says initially there is only the reactants. So this is 0.5 molar, and this is 0.75 molar. So that means initially there's no products in the system. It says at equilibrium, the concentration of the H2 is 0.44. So what I know is that once this reaches equilibrium, this one's 0.44. So we wanted to find everything, the changes that occur with respect to something that's a 1 stoichiometry. So if I look at the things that are 1, that means this would be a minus x, this would be a minus 2x, this would be x plus x, and this would be plus 4x. Okay, so I can use the column where I know everything in, and I can find out what x is. Okay, so this means that 0.44, the final concentration, equals the initial concentration plus the change. So that's pretty easy to see. When the it's 0, that means that x is 0.11. So now that I know what x is, I can apply that 0.11 to all the other concentrations. So if x is 0.11, this is 0.39. 0.11 times 2, 0.53. Did I do that right? So it'd be 0.22, yeah, 0.53. And this one would be 0.11. And then we already had this concentration as 0.4. So the question asks, what is the equilibrium constant K sub C? Now that we know the concentrations, we can just plug them into the K sub C expression, which is products over reactants. So the products are the CS2 times the concentration of H2 divided by the concentration of CH3 divided by the concentration of H2S. All right, did I write the K sub C expression correctly? What did I miss? Exponents. Raise it to the power of the stoichiometry. Very good. Okay, so go to the product side, first order. So this one would be 1, or it's first. This one would be 4, so this needs to be to the 4th power. And this is 1, so that's 1. This is 2, so this one needs to be squared. Got to make sure you do that. All right. So now that I know that, I just plug in these numbers for all these values that I have. So I've got 0.11 times 0.44. And I got to remember to take it to the 4th power. Divided on the bottom, 0.39 times 0.53. And on this one, it's squared. So it's a number. Remember, make sure you can take things to the power that you need to in your calculator. Make sure you in your calculator can come up with that number.
So, the equilibrium, that's always going to be positive, right?
The case of C,
No, on the ice.
equilibrium concentrations, yes. You can't have a negative. These can be between 0 and infinity. All right, but they can never be negative. You can't have a negative concentration. You can have a negative change, but you can't have a negative concentration. Okay? Again, you're looking at one of those problems.
So for the negative x, negative 2x, x, and x, 4x,
Yeah.
it's negative x and negative 2x because they're reacting against positive x.
Okay. So what I'm asking, or I think you're asking, is the negative aspect of it means that the reaction is going in the forward direction. So I'm making the initial assumption that the reaction is going in this direction, therefore these have to go down. And the reason I'm making that assumption is because initially these are 0. There's no choice. If there had been other concentrations other than 0, I would either have to make the assumption that's going forward, or I'd have to go solve for what Q is and do the comparison of Q to K. But on this one, I don't know what K is, so I can't compare it to Q. So you just have to make the assumptions going forward. If it came out that these would either come out if it's not correct, these, when we solve for the value of x, it could have been that x would be into when you solve for the value of x, negative x may have been this number. If that would have been a negative in here, that meant the reaction was going in the opposite direction, and these numbers would have been increasing instead of decreasing. So when you don't know, you just solve it, set it up. The math will correct itself if it's wrong. So that's not a problem. Just make the assumptions going forward. Okay. Anything else on this one? Okay. What else do you want to look at?
Number 30.
That 31 is just writing the K expression. So yeah, we can do that though. It's easy. All right. You try to do it. I said it's easy. See if it's easy to you. It's certainly easier than what we just did. Remember, it's products of reactants raised to powers of the stoichiometries. Okay? There's something you have to pay attention to in this one. What is it? The solids. The solids don't appear in the expression. Products. Reactants. Okay. The finicky or the trick for that one. You got to look at faces. If it's a solid or a pure liquid, that means that they don't appear in the case of C expression. Okay. So whenever you write it out, glance at those phases. If it's a solid or pure liquid, draw a line through it. Say again.
Aqueous does.
Aqueous does. Yes.
Did you work problem 27?
Same test?
2018.
Okay. All right, so I didn't get. Need our equation sheet. Study guides. Hopefully you've looked at the study guide at this point. So equation sheet. Okay. All right. So 27, correct? All right. So if we think about, we got to figure out what type of problem this is, and then we're going to copy something else. So it tells me it's a first order reaction, and gives the reaction, gives me the rate constant at temperature, and it wants to know how long it's going to take for the concentration to decrease to 12% of its original concentration. So it doesn't tell me the initial concentrations, it just tells me that it wants to go down 12%. So when it's something like that, assume that it's 1 molar, and then if it's going to go down 12%, what would be left is 88% of that, or 0.88. Okay, so what I want to know is the time it would take to make that change in concentration. So how long would it take to go from initial concentration of the reactant, the not, at 1 molar, and at a time x, a concentration of 0.88 molar. Okay, so this is the time we're wanting to solve for, time x. So what equation do we use to go from that relates concentrations in time? Remember what that's called? We give a name for that particular type of thing. Zoom page width. It's called the integrated rate law. Okay, so we would go back to our equation sheet. Key thing is we recognize that it's at first order. So we want to go to the integrated rate law. We want to copy that page out. So integrated rate law for a first order reaction. Maybe I can rotate it in a second. So this is first order. This is going to be my integrated rate law. We're going to solve for time. And let's go see if we can get it more. So I twist that in. So I know, think about what I do know. I know what the initial concentration is. So this is the 0.88, or sorry, at time x. This is my initial, this is 1. I know what K is. The only thing I have to solve for there is time. So the variable I don't know is what is time. How long is it going to take to get to that concentration? Okay, so I just put the equation up. So this is my value for K, and I'm going to solve that for the variable of time. So start by just putting in the numbers. So the log of 0.88 is equal to a negative, and the value of K is 0.76 times time, which is the variable I'm looking for, plus the log of natural log of 1. Okay, so that's the initial concentration. So if I take 1 and take the natural log of it, I find that it's 0. It actually drops out. Okay, so now if I want to find time, all I have to do is divide on both sides by negative 0.76. Negative 0.76 cancels out on both sides. The only thing I've got left is time. So natural log of 0.88 divided by 0.76 negative. And since this is in seconds, our time that's going to come out of that, or inverse seconds, our time is going to be in seconds. Less than 0.2 of a second. quick.
So where'd you get 1 at again?
Okay, so it doesn't matter if I would have put the numbers in, and if I would have said it went from 1/10, and still I would have got rid of 88% of it, and then what I would have had at the end would have been 0.088. Okay, so any original concentration, I got rid of 12% of it, 88% remaining. It wouldn't matter what numbers you put in, it still would have worked out. The good thing about using 1 is when I take the log of 1, that term drops out. Where if I would have left this term here and used this value, it would have been different.
So you can just pick one, like if it didn't say an initial concentration.
If it gives you the initial concentrations, you got to put the initial concentrations in. But if it doesn't, you assume 1. Yes.
Are you supposed to get it to 12%, not get rid of 12%?
Let's see. It decreased to 12%. So I read it as going down by decrease. It decreases to it, not decrease 12%. So that means that 12% is remaining. So good catch, because I definitely misread that. That means that it goes down to this value. Minor change. Almost 3 seconds. Yeah. And I read it, glanced at it, and thought decreased by, and it's decreased to. Good catch. Okay. That's an integrated rate law question. Either at the end of the chapter or multiple choice. I'm going to ask you at least one question with the integrated rate law, not multiple. The important thing is to pick up what's the order. Is it 0, first, or second order? Then you go to the table, apply, find the integrated rate law, and you look at the variables you know, and you find for the thing you don't know.
So if it was second order, what would change?
Okay, you got a question? So what would change would be which equation we would use in the integrated rate law. So we would either use 0 order, we'd use this one, first order, this guy, second order, this guy. So you choose the integrated rate laws different on every order. Okay. All right. What else?
Could you find Q?
Okay. So predictive for reactions going to go forwards. Let's see if we can find one like that. All right. So that would be in exam 3. There's case of C's. All right, let's start it off with doing that. Let's answer question 4, and then we'll solve one with it. All right, so question 4 says, which one is the following about Q versus K? So what do you think? Which of the following is true? One should stay out. Yeah, you're trying to figure out is A and B correct, but look at C. if Q is equal to K, it's at equilibrium. That's the correct answer. Okay, now what's wrong with A and B is they're reversed. Yeah, they're swapped around. So, okay, so now we know what to expect. Let's find a problem like that. Let's see, reaction. There's a Le Chartier's principle problem. But let's go do the other one, the Q problem first, and then we'll come back.
Q is less than K, it goes right.
If Q is less than K, it goes forward. That's correct. There it is. So there's got to be a problem. Problem number 11. Okay, so we've got an equilibrium. And then it tells us the initial concentrations of the reactants, and it wants to know which one is true. So which way is it going to go, basically? Okay, so first thing we do is we write out our Q expression. The initial glance I need to look at things is everything in phase? It could be counted as Q expression. And I see I got a couple of solids in here. They're not players. Okay, so my Q is just going to be based on the things that are in the reaction. So the products, it's the concentration of the CO2 and the concentration of the water squared because of the two stoichiometry, and the reactants is just the concentration of the methane, the CH4. I know the concentrations for all of these. So the methane is 0.22, goes on the bottom. The CO is 0.67, and the concentration of the water is 1.3 molar, and I've got to square that. So I get a value for Q. And I get 5.15 is my value for Q. And then I need to do the value or comparison of Q versus K. So it's 5.15. If I look in the table, I see that K is 1.1. So anybody else come up with my Q? Did I do the math right? Okay. So in this case, Q is greater than K. So that means the reaction is going to proceed in the reverse direction. So it's going to shift towards the reactants. Choice B.
C, is that even a possibility?
Which one?
C, answer choice C.
No. Now that would mean that K sub C is increasing, and the only thing that would do that is change the temperature. Okay, so we pointed out this Le Chartier's principle problem. There's a couple of those. Let's look at doing those right quick. So those were something we just talked about in class. Okay, so look at 7. So you got a system that's in equilibrium. What would be the effect of removing some water from the system? So I'm going to get rid of some of the H2O. Which way would it shift? Okay, it's going to shift in the forward direction. So towards the products. Be choice A. Yep. All right. Number 8 says you got a system at equilibrium. What would be the effect of reducing the volume of the reaction? And you had a clicker question almost just like this.
No effect.
No, but
Okay, why do you think no effect?
that equal number of moles.
Yeah, so the solids don't appear, they don't influence it. We're concerned about only the gases. I've got 1 mole on this side of gas, 1 mole of gas on this side. When it's equal moles, there's no difference, there's no effect. So yeah, choice C.
But reducing the volume would make it go to the side with more.
Reducing the volume would make it go to the side with the fewest moles. So let's say that there were 2 moles of gas on this side. Let's say this is a 2. All right. So if that were the case, we reduce the volume. What it wants to do to release the stress is get rid of some of those moles of gas. So it would run in this direction, in the reverse direction. It's trying to get back to where it was, that status of equilibrium, as much as it can. Okay, what else? Make sure that you review a K sub C to K sub P conversion. If you look at all the old tests, you're going to see some questions like doing that. And it seems so simple, you forget. Make sure you work 1 or 2 on the old tests that know how to use. Number 2, just a comparison of the number of moles, delta N. So there are 3 moles of gas on this side. And yeah, so that's a liquid. It doesn't count. 3 moles on this side and 6 on this side. So it'd be a -3. So it's products minus reactants. Yeah. Always got to look at your faces. Okay. So only something else to go to.
Delta M doesn't have a sign.
That's correct. K doesn't have units. Capital K. The equilibrium constant doesn't have units. It's units. Right, y'all want to do a calculation with that? One of those, K sub C's, K sub P's?
Yeah.
All right, so there's looking at an example of 1. So let's put the equation on the page, and then let's go back to our handy-dandy equation sheet and look at our relationship. Our relationship between K sub C and K sub P. Got that. So, P a bit smaller. Yeah. Okay. So what it does is it gives me the K sub P value, so I know what this term is, and what I'm looking for is what is K sub C. Now the temperature is already in Kelvin, so that's good. I know what T is. Our constant that we got to use for R, so that's where we have to go back and think about which value for R do we use, and go back and look at our table. And the R, we've got 2 R's. We've got one that's a thermodynamic R that we use with the activation energies, and we've got one that's the R gas constant that we use with the ideal gas law. This is involving the gases. So this uses this R constant. For the life of me, I don't know why they couldn't call one of them Q or some other letter in the alphabet, but we stuck with R. So you got to know which R that we're using. So we're using the 0.08 one in our calculation. So we know what it is. That's the important thing. All right, so we know what R is. Okay, so first thing I'd want to find out is what is delta N. So delta N is the number of moles of gas product. So it's 3 minus 2, so it's a positive 1. Okay, so on this I'm looking for K sub C. So K sub C is going to be K sub P divided by RT raised to the delta N power. At that point, it's just a matter of plugging things in. So 3.35 or 3.3 times 10 to the minus fifth. R is 0.08206 times delta or times T, which is 700, and it's raised to the 1 power, which don't even have to write out. And I get 5.74 times 10 to the minus 7th, choice B. Question on that one? So that's almost a guaranteed problem. I'll give you the information, like a case of P, solve for a case of C. R, and like in this time, I gave you case of P was given, and you had to find out what is case of C, one way or the other. But something about that relationship. Okay? What's next? Okay. Which problem?
Number 17.
Right. Okay, so this one is a little different in that it gives me the value of K sub P. So I know what K sub P is in the problem. So that's given. And it gives me the partial pressures of some of the components, and it wants to know for the other ones. So I know the partial pressure of the SO2. I know the partial pressure of the O2. The one that I don't know is I don't know what's the partial pressure of the SO3. So if I think about what does the KP mean, the KP is the ratios of the pressures instead of concentrations in atmospheres. So it's the partial pressure of the SO3 squared to represent the product divided by the partial pressure of the SO2 squared times the partial pressure of the O2. And it's a one stoichiometry, so it doesn't have to be squared. So what I'm looking for is I'm trying to find out what is the partial pressure of the SO3. I know what everything else is. Okay, so it's just a matter of rearranging and solving for that. So if I rearrange, I multiply these terms to the other side. So the partial pressure of the SO3 squared is equal to K sub P times the partial pressure of the SO2 squared times the partial pressure of the O2. So I know what all these numbers are. So K sub P is 0.3 0.45. Partial pressure of SO2 is 35 atmospheres. I've got to take and square that one. And the partial pressure of the O2 is 15.9 atmospheres. Okay, now that equals to the partial pressure of the SO3 squared. So the way I get rid of the square is I take the square root of both sides. So if I take the square root of both sides, I get 82. Yep. Plus, want to work another of some type of problem?
We work a problem where it's like, can you go back to the equation?
Yep.
Where it's like the ln k2 one, but we're able to like rearrange it.
Like this one down here?
No, go back.
Okay, an Arrhenius equation.
Yeah.
Okay, so let's, that we got one like that on the test. All right, so let's see if we've got a, there's a breathalyzer disappearance. Okay, so problem 28, gonna be a reaction like that. It gives me the rate constant. No, that's a time one. So let's go back to the next year. That's first order decomposition. That's an integrated rate law problem. So it's 27. Okay, 28. Smaller. Okay, so on problem 28, it says it's a first order reaction. It gives me the activation energy. So if I just want to check off the things I know and label them. So the E sub A, I know what that term is. It tells me that the rate constant at 30 degrees. So I'm gonna call this one T1. So T1 is this value, and I'm going to call that K1. So I know T1 and I know K1. It wants to know what is the rate constant at 35 degrees. So that would be solving for K2 at a temperature of T2. All right, and I know what T2 is. Okay, so I know what R is. So now R is going to be the 8.314 value of R, joules per mole degree Kelvin. So I got to switch to the thermodynamic value of R. The only thing that I don't know in this is what is K2. So I'm going to solve everything on the right-hand side of the equation, find a number, and then solve and find out what K2 is. So the first thing I need to do to make this work is I need to know what the temperature is in Kelvin. because I get it in Celsius. So I take 30 plus 273, and this was 303. And then 35 is going to be 308. Okay, so I know what my temperatures are. The other thing, when I do the activation energy, to make it cancel out with R, I need to put it in joules. So multiply it by 10 to the third joules per mole. And we've been going on the last test we did this. Some of you went the wrong way. Make sure you multiply it by 10 to the third. So now we just plug in and start solving. K2 is what I'm solving for. K1 is 9.8 times 10 to the minus third. Right, so activation energy R is 1.26 times 10 to the third, divided the value of R is 8.314. 1 over T1. T1 is 303. Less 1 over T2, which is 308. All right, play along on your calculator. So everything on the right-hand side is just going to become a number. So I'm going to take 303, inverse, less 308, inverse, get what that is, times 126 e to the third, divide it by the value of R, and everything on the right-hand side is 0.811 with an insignificant 9. Okay? So now I need to, anybody else get that? Yes? Okay. All right, so now I need to find out what K2 is. So to get rid of that, I need to get rid of the natural log. I need to take the anti-log of both sides. So the anti-log of a log is just going to be K2 over this constant. So this is 2.25, then significant 2. So now I just take and multiply this term to the other side times 9.8 times 10 to the minus 3. We only have 2 sig figs. And the units are going to be the same as it was. So it was inverse minutes here. Usually we talk about inverse seconds. This is a slow one. It's inverse minutes. So the units would be the same as the inverse minutes. Okay, does it make sense that the number goes up? The temperature is increasing, so I expect the rate to constantly increase as well. So the number is bigger. That makes sense to me. Okay. And again, if you're struggling on the math on these a little bit, go back and play this video through. Make sure you and your calculator and crank every one of these numbers out. And I say not struggling with the math of it, if you're struggling with your calculator. I make the joke at the start of the year, your calculator has to be your best friend. It gets where it's not so funny after you miss a couple of points on every one of those questions at the end.
I was looking down for data too.
Okay, I took the anti-log. That's from putting this as my calculator, comes that. Okay. All right. What else?
do a half-life?
Someone? Half-life is probably exam 2. Here's an example of one of the ones like I gave you all the plots, and based on which one was linear, from that you had to determine the order. I talked about those in class. But I gave you a plot of the data in all the ways. So concentration versus time, natural log of concentration versus time, inverse concentration of time. This one's not linear. This one's not linear. The one that's linear was the natural log of concentration versus time. That tells me it's first order. Okay. So how would I know that? Well, I could go back and look at those equation sheets and see that when it's the natural log concentration versus time, that's the one's first order. Okay. All right, but that was a side track from where we're trying to get. So we were looking for. There's a half-life problem with that one. So let's do this one. So it's try to get all of it in there. Okay, so the question asks a couple of different things. So it asks what is the order of the reaction, and the fact that this is the one that's linear tells me that it's a first order reaction. If this is the one that was linear, it would be a 0. If this is the one that was linear, it would be a second. But this is the one that's linear, so it's first order. So what's the order? It's first. So first order with respect to the reactant, which is this guy. Okay, so the second thing it wants to know is it wants to know, move it up, stand my page down, there it goes. It wants to know what's the half-time for this reaction. Okay, so for a first order reaction, the equation that we had, I'd go back to my handy dandy equation sheet and go to the top of here. Half-life is equal to 0.693 divided by K. Okay, so the slope is equal to a negative K, so I've got to take those things and put them together and apply it to the problem that I've got. All right, so the slope is equal to a negative of K, so that means for this one that K is equal to a negative of a negative, put that on top of it, point, I think it's 46 something. Can't see what's underneath it. There it is. Negative 461. So that means that K is a negative or a positive 0.461. Negative and negative make it positive. So the half-life was equal to 0.963 divided by K. So it'd just be the 0.963 divided by the value of K, which is 0.461. So it's a second and a half maybe. I'm a very good guesser. Second and a half. Okay, so that's an example of applying it to find out what the half-life is. Another portion of that would be on part C. It says how long would it take for 92% of the compound to convert So if it went forwards at 92%, at that point it's the integrated rate law. We've already done one like that. So let's see if we can find a different half-life problem. Okay, there's a couple. Okay, so on this 21, it says the concentration of the reactant is 6.25%. How many half-lives as it went through? So it's really not much as a calculation as it is just understanding what half-lives are. So at 100% is where you start, and when you get ran out of 50, go down to 50 of that, you've went to a half-life. So that takes one half-life. I go to half of that, so it's 25% of the initial. I've done another half-life, and then half of that, it's 12.5%. That took another half-life. Half of that again, that's 6.25%. That took another half-life. At this point, you just calculate the half-life. So I had 1, 2, 3, 4. Took 4 half-lives to get to that. So if I know the value of the half-life in minutes or seconds, just multiply by 4, and that's how long it took to get. All right. 22 wants to know what's half-life of the reaction if the initial concentration is a certain value. And it gives me the rate constant, it gives me the value of K. So I know what K is for this zero order reaction. I know what the original concentration, A naught, is. So I want to apply it to the equation. So I've got to go back to my equation sheet, and I've got to look for a zero order. And for a zero order, my relationship is that the half-life is equal to the original concentration divided by 2K. So it just becomes plug that in. So the original concentration is 0.33 molar. 2 times the value of K, and the value of K is 0.54 molar per second. Molar cancels out. Seconds go to the top. So it's going to be so many seconds. It's going to be a little bit less than the original value. What else? He said it is. Okay. 11:30 tomorrow. Bring your scan drawing. Again? Good point. Yeah, no day off. Yeah, tomorrow, bring your chapter 16 notes. Start on chapter 16. Not used to doing that review as far in advance, but yes, Thursday.
Tomorrow,